Happy Tuesday. Looked at sequences last time. We now get to move on and examine series. Series takes on this form. Summation from some starting point to infinity of a term, a sub n. All right. The starting point is typically non-negative. In fact, the ones that we're going to be looking at will always be non-negative. Usually 0 or 1. Well, it's infinite, right? So we're summing up an infinite number of terms. That's the idea. Few properties of series. Really just one that I want to look at right now. They're linear, which means they satisfy the linearity properties. Right? Sum of a sum, that sounds weird, is the sum of the sums. And you can factor constants out. Right? Makes sense because you're allowed to factor out of summation. Right, these should be fairly obvious. The first one is the associativity property. And the second one is the factoring property, factoring distributing. There will be two other properties that we look at later, specifically differentiation and integration. We'll deal with that when we get to it. We want to examine this series for convergence. A series converges if the limit of their partial sums converges, and they converge to the same value. In such a case, we say that the infinite sum is equal to that limit. So that is what we mean when we say evaluate an infinite sum. If the limit does not exist, the series diverges. Okay. Well, we can factor 1/5 out of that sum, can't we? We're left with 1 plus a fifth plus a 25th plus so on and so forth. It's just a fifth to the 0 plus a fifth to the first plus a fifth squared plus so on and so forth. We can write the sum as a fifth times the sum n equals 0 to infinity of 1/5 to the n. This is a special type of series. What's this series called?
Geometric series.
This is geometric. It will converge when the absolute value of r is less than 1. Furthermore, it will converge to the value C over 1 minus R.
So did you factor out the 1/5 specifically for this one?
Yeah, so I can start at n equals 0. There is a formula for if it doesn't start at 0. But I just find it easier just to factor it out and force it to start at 0. I do provide both in the video. This is the first thing I would write down on my separate reference sheet. So with that, our series will be 1/5 times 1 over 1 minus a fifth. So 1/5 times 1 over 4/5. Which is a quarter. So the series converges. I'm going to show that this series diverges. The divergence test. The actual statement is if the series converges, then the limit as n approaches infinity of a sub n is equal to 0. However, that statement isn't too useful as it is. In logic, a statement is always logically equivalent to its contrapositive. Contrapositive our statement is if the limit as n approaches infinity of a sub n does not equal 0, then the series diverges. That is the more useful statement. There's the first of 7 tests. Note that divergence test can only test for divergence. It will never give you convergence. If the limit is 0, this test is inconclusive. It does not automatically mean it converges. And yet every year I teach this without fail. I'll have someone show the limit is 0 and then conclude it converges. Let's try and write this in summation notation. What do we notice about the denominator? Denominator is the power of 2. What about the numerator? One, 3, 7, 15. What about the 1? Okay, I see what you're doing. Again, that's recursive. Right? Multiplying the previous numerator by 2 and then adding 1. How would we define it if we're not looking at previous terms?
Yeah, minus.
Isn't each numerator just 1 less than its denominator? There's actually 2 ways now to go about showing that this diverges. First is the divergence test. What's that limit? It's 1. Which does not equal 0. And so our conclusion is the series diverges by the divergence test. The other way to look at it. Oh, wait. This isn't going to work out the way I wanted it to. Oh, yes, it will. Yes, it will. So split it into two fractions. You're then allowed to split it into two summations because summation is linear. These are both geometric. First one, r is equal to 1. Second one, r is a half. That second series converges, doesn't it? What about the first series? Why? Absolute value of r is not less than 1, so it has to diverge. We wrote our series as the sum of a convergent series and a divergent series. Hence, it has to diverge.
So because they're two different things, divergence and convergence, so one is divergence, that means that it's divergent series.
And that means it diverges.
Oh. So are we just forgetting about the second part? We're just looking at the first part of it, where it's divergent.
Well, it's the sum of a divergent and a convergent, which diverges. If there's a sum of all convergents, it would converge. Right? The fact that even just one of them diverges means the whole thing has to diverge. So remember, geometric series is a sum r to the n, right? Some number raised to the n power. That number here is 1. It will only converge if the absolute value of that number is less than 1. You can also just look and go, isn't this just summing 1 an infinite number of times? So it's 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. That clearly diverges. Well, I shouldn't say that because there's a resultant string theory that isn't really obvious. Examine the series 9 minus 12 plus 16 minus 64 over 3 plus 256 over 9 minus so on and so forth for convergence. Nine minus 12 plus 16 is 13. We can factor out a negative 64 over 3. We're left with 1 minus 16 over 3 plus so on and so forth. If you keep going, you'll get minus. No, that's not 16, that's 4. Why won't you erase? One minus 4/3 plus 16 over 9 minus 64 over 27. Those are the next couple of terms. Negative 4/3 to the n.
Can you clarify how you like got that equation?
What equation?
Like 13 minus 64 times like the series.
Well, 9 minus 12 plus 16 is 13. So that's where 13 comes from. The remaining terms all have a 64 over 3 common. Factor it out. And you have 1. I'm actually factoring out negative. 1. Then 256 over 9, factor out 64 over 3. 4/3. Well, it's going to follow the pattern. Next will be 16 over 9. Next will be 64 over 27. And it's alternating. Which is negative 4/3 to the n power.
I realized you're writing it in this form so that you can like have it in the normal geometric series form, but wouldn't it be easier to first write it as like 4 to the n over 3 to the n minus 2?
Your n would start at 3, right?
Yeah, mine would start at 0.
Well, if it's starting at 0, it's not 4 to the n over 3 to the n minus 2.
Why
4
not?
to the 0 is not 64.
Yeah, but I'm starting with the first term. None.
No, those first 3 terms don't fit any kind of pattern. That's why I combined them into 13.
But they do. If you compute 4 to the 0 is 1, 3 to the 0 minus 2 is 1 over 9. And so 1 over 9 is 9. And I missed the negative in my series. So you'd have to add that, but
You have what, 4?
like you're still multiplying by 4/3 to get from term to term there.
Hood. That would give you this.
Okay, you just need the negative.
Oh no, I'm sorry, it wouldn't be 1/9, it'd be 9. Would it be? Be 3. Yeah, it'd be 3 to the n times 3 squared, yeah, so it'd be 1/9. That was right the first. No, times 1/9, yeah, it should be 9, right? That also works. Which clearly diverges.
You do need the negative.
Well, there would be a negative, yeah. I can just put the negative to the 4, doesn't matter. Just to make my life easier. Yeah, that would work. Point I'm making here is it doesn't matter how many terms you pull out. The end result's the same. All right, so if you do this or you just combine the first 3 terms, the end result's going to be the same. As long as it's a finite number of terms. Leave that blue separate. That series is geometric, with R being negative 4/3. Absolute value of negative 4/3 is larger than 1. So that series diverges. So what we have is a number minus a number times something that diverges, which has to diverge.
How did you know R was that is coming from the summation equation?
It's being what's raised to the nth power, right? That's what a geometric series is.
Okay, and then the last thing is just, and it's diverging because it's not less than one.
Absolute value is not less than 1. You can also easily do it just by taking its limit. The limit does not exist. Does not exist is not 0. Hence it diverges. Once we evaluate this series, what are we going to have to do first?
Probably pull the n up from
What do you mean by pull it out?
as in make it -1/2 to the n.
That which you could also just do in your head. Now what?
No.
Well, I'm not asking to test. I'm saying evaluate it. Which technically means evaluate if it converges.
E over
What's C?
the constant.
What's R? This is geometric. The sum evaluates to 2/3.
See the one minus. Let's see.
What's your R to the n being multiplied by?
1. That's
So that's C. This one's cool. Right, 0.9 repeating is a fraction. There's actually two ways to go about this. I'm obviously going to use the method that requires series. But there's an algebraic method. Well, 0.9 repeating. Right, 0.9 plus 0.09 plus 0.009 plus 0.0009. In fraction form, 9/10 plus 9/100 plus 9/1000 plus 9/10,000 plus so on and so forth. Factor out of 9/10. One plus 1/10 plus 100th plus 1,000th plus so on and so forth. Nine tenths times the infinite sum. Isn't it 1/10 to the n power? Which is geometric. With r being 1/10. And c is 9/10. So it's 9/10 over 1 minus 1/10. 9/10 over 9/10, which is 1. 0.9 repeating is equal to 1. Of course, that is only true if the 9 repeats forever. If you say it cuts off at any point, it's no longer equal to 1. Determine whether this series converges or diverges.
converges.
You have to explain why.
Because you can show that it's always less than 1/n squared. And that converges.
Sorry, we haven't covered the comparison test yet. To write this in series form, n equals something to infinity.
Over 4n squared minus 1. You might have to like mess with the where you start it.
Oh, what am I doing? X squared 936. Yes. That's not how I'm going to write it, though. Where'd your n start?
One.
Don't write it in factored form. There's a reason for that. Look what happens. What is that limit? The divergence test fails. Right, so that means this could either converge or diverge. So we're gonna have to do something else. There's only one other method we have at our well, two other methods. One of them's not gonna work. This is not geometric. That leaves only one other method. We have to calculate the limit of the partial sums. If that limit exists, then we have convergence. If that limit does not exist, we have divergence. That is why I wrote it this way. Think way back. What was it? The third week? The method for evaluating an antiderivative of a rational function. We write the rational function as its partial fraction decomposition. That's what we're going to do here. And it should not be difficult for you to see that this leads to A being a half and B being -1/2. Taking out the 1/2. The series can be written as a half times summation n equals 1 to infinity, 1 over 2n minus 1 minus 1 over 2n plus 1. We want the formula for the partial sums. It will be 1/2 times. When n is equal to 1, we get 1 minus a third, don't we? When n is equal to 2, a third minus a fifth. When n is equal to 3, the fifth minus a seventh. And finally, when n is big N, all of your middle terms drop out. Right, negative third plus a third, 0. Negative fifth plus a fifth, 0. Negative seventh plus a seventh, 0. So the partial sum sequence can be represented as the sequence of n over 2n plus 1. Right, that is an explicit formula for the nth term of our sequence. Negative third plus a third. Negative fifth plus a fifth. Negative seventh, next will be plus a seventh. Right, and that keeps going until all you're left with are the two n terms. This type of series has a special name. It's called a telescoping series. We now need to take that limit. What is that limit? What is it? It's a half. The series converges. Specifically, the series converges to 1/2. It's a rational function, right? What's the degree of the numerator? What's the degree of the denominator?
So one.
Are the degrees equal? Then your limit's the ratio of the leading coefficients. You could also just use L'Hopital's rule. Derivative of the numerator is 1, derivative of the denominator is 2. You're left with the limit of 1/2, which is a half. Determine whether this series converges or diverges. Okay, we're going to write this in series notation.
B to the 1/n, and then starting at 0.
Oh dear.
I mean, 1.
That's not geometric. That doesn't work. So we have two options. Divergence test or calculate the limit of the partial sums. I really don't want to try and find a formula for the partial sum, so let's hope that divergence test works. If not, we cry. So we're looking for this limit. Will wind up being 1. Isn't e to the ln of 3 to the 1/n 3 to the 1/n? So what's that limit? 3 to the 1/n. That's why we're doing this. I could probably also argue that 3 is, could I? 3 is an exponential. 3 to the 1 over n is exponential. Base 3. Could I do that?
Try to prove what?
Because then I could just pull the 3 out immediately. Because exponential functions are continuous everywhere. Yeah, no, I can't do that. I do have to do it this way. That's a bummer. That limit is e to the 0, which is not 1. Oh, I'm sorry. It is 1. It's not 0. Right, limit of log 3 over n as n goes to infinity is 0.
You just said that the nth root of any number greater than 1 is going to be greater than 1.
Well, true, how does that help?
Because that means the limit, as you take more and more roots, it has to be greater than 1.
Well, the limit's not greater than 1, is it?
Okay, well, not the limit, but the limit has to be.
The limit is equal to 1.
Yeah, but it can't be below 1, is what I mean.
You could try and argue that. But that's more work than just calculating the limit. Like, so you'd have to argue why it's the case that the limit can't be less than 1.
I mean, it seems pretty obvious.
The most obvious things are usually the hardest to actually prove. So you'd have to prove it using properties or definitions of limits. It's just easier to calculate the limit. We still have time. That's nice. Guess we could get more. Oh, those are boring. That one's not. Neither of those. Okay, I guess we get more practice doing this. Good questions so far. Sigma notation is just summation. Right, because that sum symbol is a capital sigma. Some of these are boring. I mean, these were that's why would they even throw that on there? That wasn't challenging at all.
-1 parentheses to that.
Depends what's your end starting at. Hmm? Doesn't matter. 2, 0, same thing. Both correct.
And
What's your end starting at?
I started 1.
You start that series, you can make the denominator n+1.
Good. That means we have to erase more than I want to. There's a quicker fix. Yes, you could also write -1 to the n over n+1 and starts at 0 to infinity. It's the same thing. Right, so more than one way to represent a series. Could also done that as n+1. I could have been really crazy and started at n equals 6 and tried to write something.
Sine 1 over n starts at 1.
These are boring. No challenge whatsoever. We get the first four partial sums. So what S1 be? What's S2? What about S3?
6,
S4?
10.
This summation. It's particularly interesting. It can be shown if we take the Riemann hypothesis to be true. And this is also a result of string theory. That sum winds up being negative 112. I do not accept that result. Because it goes against everything I've learned. Exactly. It's been proven. But again, it's assuming the Riemann hypothesis is true, which we have not yet proven. And this is also used in string theory. Don't like that result. I still say that's not true. There's a flaw somewhere. Oops. What is the first partial sum? I know how to draw a confused face. What about the second? Third?
Let me see.
Fourth?
By 12.
Do you remember what a partial sum is? So the nth partial sum? We did go over it. It was the very first thing. Instead of infinity, it just goes to big N. So for S1, it just is n equals 1 to 1. Right? That's a single term. For S2, it'd be n equals 1 to 2. So that'd be 1 plus 1 over 2, right? For n equals, for 3, it'd go n equals 1 to 3, so it'd be 1 plus a half plus a third. But notice, each term of the partial sum is the previous partial sum plus the next term. Right, so you can also just say S3 is 3 halves plus a third. S4 would be S3 plus a fourth. So what's S1?
1,
What's S2?
1,
What's S3?
0,
What's S4?
0.
I think S5 would then go back to 1, wouldn't it? S1. Was it? What's S2? What's S3?
-1.
Be -1 again. What's S4? Be 0 again. The sequence is -1, 0, -1, 0, -1, 0, -1, 0, -1, 0, -1, 0, so on and so forth. If I made a slight change and made that n-1 instead, it would be what? 1, 0, 1, 0, 1, 0, 1, 0, right? Well, we can easily tell that those last two diverge. Right? Both of those sequences diverge. So the series would diverge. Should be fairly simple to see that that second one is also diverging. Actually, it should be fairly simple to see that both of those diverge. Unless you're crazy and accept that that sum is -1/12, in which case it would converge, which doesn't make sense. So all four of these actually diverge. Other interesting ones. Not really. Well, I guess I could do that one, but that would take too long. Questions on series. So there are two things that should be on your sheet. Definition of geometric series and when it converges. And the divergence test. What we look at next is we're going to split series into two parts. We'll look at series strictly with positive terms, and then we'll look at alternating series more in depth. And we'll come up with several more tests for convergence. These tests will not tell us what a series converges to. One will. The integral test will. But for the most part, they just tell us whether it converges or not. If you want to determine what it converges to, you have to do the sequence of partial sums and take its limit, which is a bloody nightmare for most series, especially once we start getting into the ones that have factorials.
If the sum of A and or A is then limit AN is 0. If limit AN does not equal 0, then it converges. That's the divergence test. That, yeah, yes, that's right. Okay.
This table comes around, it's going to be this morning.